Sunday. I'm gonna hang out with my mom. She lives in near Akron. No, I grew up in California, but my mom moved here when I went to undergrad, and so she followed me, or I followed her, depending on. Well, so all of her family has lived here the whole time, and so she wanted to move to be closer to me. What? I actually gave part of this talk like 30 minutes ago. Yeah, I thought that it was going to be different, but yeah. Yeah, sure.
Good morning, everyone. So let's get started. It's a pleasure to have Chelsea Finn with us. So let's welcome back Chelsea to MIT. So she was an undergrad here. So welcome back, Chelsea. So Chelsea has done some very great work, both in robotics and reinforcement learning and machine learning. One of her first papers was a paper which was mapping pixels to torques, right, way back in 2015, right, and that was, well regarded as one of the papers that started getting people interested into doing machine learning with robotics from high dimensional observations in the new deep learning era. After that, Chelsea had many other works which have been, quite influential. So she did work on inverse cost learning. Then in 2017, they had the mammal paper doing meta learning, right? And around that time, there was also work on building forward models and building models which can predict what happens in the future, using them for control, and the list goes on and on. And then Chelsea has received multiple awards, including the Sloan Fellowship, the IEEE RAS Early Career Award, and many others. So Chelsea, welcome back, and very excited to hear your thoughts on robot learning. So please take it over.
Awesome. Thank you, Pulkit. Really excited to be back on campus. Today, I'm going to talk about some of my perspectives on generalization and dexterity in learning robotic skills. So to set the stage for the talk, I'd like to show some videos of what robots can do today. And so these are actually not even today, like 7 years ago, actually, for this first video. And I think that we've seen examples of robots being able to do things that look really impressive, like being able to use tools to lift an object or various stunts on a humanoid robot. But there's also a little bit of a catch. So these are undoubtedly really impressive, but the example on the right was tuned for that environment, and the example on the left was trained using 15 minutes of data in that particular environment. So robots today, they can perform complex, impressive maneuvers in narrow and controlled environments. And what I've been really excited about trying to figure out for the last several years is how robots might be able to generalize to the real world. Now, I think that we have a bit of a challenge, especially in terms of machine learning for robotics, where we often train robots in very narrow distributions, such as in a lab environment, and then hope that they'll be able to handle real world situations with lots of different objects, environments, and so forth. And to try to now enable robots to generalize to the real world, I think that we first need to broaden the training distribution. And I think that broadening the training distribution is arguably one of the only recipes that's enabled AI systems to handle kind of in the wild scenarios like machine translation systems, computer vision systems, and so forth. And I think that training on a broader data set will be necessary for enabling robots to get into the real world, but I don't think it's going to be sufficient for enabling robots to generalize to the real world. And to get into the real world, I think they're also going to have to generalize beyond the distribution that they were trained on. And this is where things get a lot trickier and a lot more challenging. And I think that one of the reasons why this is really challenging is that I don't think we can actually even anticipate every possible scenario that a robot might encounter in the real world. And so if we can't even think or kind of imagine or anticipate what the robot's going to see in some test scenario, then how are we going to prepare it for that sort of scenario? I think there's a lot of disagreement in how we can generalize beyond the training distribution, but what I'm most optimistic about and what I'll show some results on today is whether we could allow robots to train at test time as well. And if they could adapt to their scenarios on the fly at test time, then they don't actually have to anticipate every possible scenario in advance. They can actually just use some data, a small amount of data collected in that new scenario at test time to handle that scenario. Cool. So this is most of what I'll talk about today. I'll talk about an effort of trying to train robots on broader data, an effort on trying to allow robots to generalize beyond the training distribution by adapting at test time. And then lastly, if there's time, I'll revisit dexterity with an eye towards, in the future, enabling both dexterity and generalization. Awesome. So let's start by figuring out how we can train on a larger and broader data set. So to start, I think that in robot learning research, typically what we do is we will have a task that we want the robot to do using some algorithm. And so we'll collect a data set for that project, use that data set, write a paper about the robot using that data set to learn something. And then we won't use that data ever again. We'll just start a new project and collect a new data set for that project and kind of rinse and repeat. And we'll do this for each and every project. And I think that this is problematic from a number of standpoints. If you imagine a machine learning researcher trying to solve a computer vision problem, if they had to recollect ImageNet for every single project, they probably wouldn't get very far. And so I hope that as a robotics community, we might be able to move more towards what machine learning researchers do, which is to collect or curate a large data set once, and then reuse that data set many different times in order to get a good model, or even better, don't even train on that reused data set, just download a model that was already trained on that data set and use that pre-trained model. So really the essence of this is whether we can start to share data and models across institutions in robotics rather than having our own data sets collected from scratch. And if we can do this, I think we can make a lot more project as a community collectively. Cool. So this is actually a slide that I made, I think actually a couple years ago at this point, but I'm actually really excited that we've started to make progress on sharing data across institutions through a couple different efforts.
想到明天早上要去，我还是学校集合吧？你觉得呢？
没查，
Whoever's on.
就差半小时。
我上回
Actually, I don't think I even have permission to mute them. So I'm not the host. Yeah, I'll let you do it. Okay. So what's stopping us from sharing data across institutions? So I think that our picture looks a lot like this as an analogy for the current data sets in robot learning, where each robot data set that we have corresponds to a different island. For example, this might be the bridge data set collected at Berkeley. This might be the MIME data set collected at CMU, the RoboTurk data set collected by some folks at Stanford, and so on and so forth. And I think that this is really challenging of a picture to deal with, because inevitably when we want our robot to do something new, we might be somewhere out in the ocean over here where the existing data sets that exist are a little bit too far away from what we want to do in order to be useful for that scenario, and so on and so forth. And so I'm going to talk about two different efforts. The first effort that I'll talk about is trying to essentially build a bigger island and also standardize a platform such that some researchers might gravitate towards that island and start to be able to reuse data across institutions. And then the second effort that I'll talk about is whether we can take the islands that we have already, which are in many different formats and many different servers and so forth, and actually put it in a common place so that we can start to train across these different islands of data. Cool. So what we think we need is the last thing that I mentioned, which is a kind of a common data hub for the existing robot data so that we can actually start to train models across these data sets. As well as data from, as well as kind of a larger island, data from lots of different environments of lots of different tasks, and ideally kind of a centralized effort that might start to kind of collect that island of data, that larger island of data. So the first effort that I mentioned, our goal has been to collect manipulation data in at least 50 different household environments. And to do this, we aggregated 70 people from 18 different Slack organizations, and we actually first agreed upon a common platform that we at least all would gravitate towards, such that we could hope that this data might be especially useful when sharing across different institutions. This project is still ongoing. It's coordinated by Sasha, but so far we've collected more than 30,000 demonstrations in 600 different scenes on a single common platform. And what's exciting to me is that this wasn't just collected at one institution in one place. It was actually collected by 11 different labs on this single common platform. And you can see some examples of the demonstrations on the right. So this is an ongoing effort to try to build a larger island that I hope that might allow us to share data across institutions. But what about also using the data that we already have? So to do this, we need to try to put all the data in a common format and actually put it in a centralized place, and then start to train models on that data. Now, these two steps sound pretty straightforward, but actually putting the data into a common format is a rather arduous process. And I think that most graduate students and undergraduate students probably wouldn't be interested in kind of downloading all these data sets and doing the work of converting the data to a certain format and everything. And so what we did, and this was a really a big effort that was certainly not just me, was to actually put all this data in a common format as a community. And so rather than having one person try to put all the data in a common format, we reached out to lots of different people from lots of different institutions, asked them if they'd be interested in contributing data to this effort. And if so, they could put it in a common format, be a co-author on this really massive effort. And then we could start to train models on that data set. And this effort, as of Sunday, it's still growing, hopefully. It has 174 co-authors from 34 research labs and at 21 different institutions. So let's talk a little bit about this data effort. So the aggregated data that comes from all these different institutions has more than 1 million different robot episodes, most of which are teleoperated demonstrations. This data spans 22 different robot embodiments, including Franca, this Google robot, the Hello robot, UR, Canova, and some platforms that I've never heard of. It also comes from 34 different research labs and spans 300 different scenes. So this is a single aggregated data set of all the existing data, or not all of it, but a lot of it that's out there. And it's now open source, and you can download it and use it and try to actually start to study what it is like to use these really large scale data sets in robotics. It has, per robot embodiment, the Franca is the most represented with more than 20 different data sets in the aggregated data set, but there's a long tail of other embodiments. There's lots of different scenes that I mentioned in the data set, and a lot of these come from either the Franca or the Google robot. But even then, almost half the data set is a little bit more uniformly covers all of the different other embodiments. We also see lots of different kind of skills that are represented in the data, ranging from picking, moving, pushing, placing, wiping, dropping, and so forth, as well as a large number of different objects in the data set as well. And if you want to use this data set, it's all stored in an efficient TF record file. You can download it with Python code and load it with these few lines of Python code. And there's also a fairly easy workflow for trying to filter out data based on the embodiment, based on the cameras, the collection type, and so forth. Cool. So that's all on the data side of like aggregating all these different islands into a single hub of data. Now, a really big question is, can we actually train models on data that comes from different institutions and data that comes from different embodiments and different robot platforms? So to study this question, we took some architectures from previous works. We took the two transformer-based models, RT1 and RT2, and we chose these because they have a high capacity for using broad data. And the input to both of these architectures corresponds to the RGB image and a text instruction, and the output is discretized end effector actions. And so this is a fairly standard language condition policy. We train this with supervised imitation learning and the RT1 is trained with like ImageNet pre-training for the ConvNet backbone and kind of language pre-training for the instruction embedding. Whereas RT2X, this is actually a little bit different. It uses actually a pre-trained vision language model called PolyX, the pathway language image model, and actually co-fine tunes on both the robot data and the vision language data, following the recipe in the RT2 paper. And then the last thing that I'll mention is we didn't train on all the data. We trained on a subset of the aggregated data set that I mentioned. Specifically, we picked a subset that has a single robot arm, mostly parallel jaw grippers, and that has language annotated demonstrations. Even though we're only using a subset of the data, the subset is actually still quite diverse. And so these images cover some of the diversity in that subset. Cool. Now, unlike typical robot learning efforts, the way that we actually train and evaluate these models is a little bit different than normal. So the training was done for these models at Google. And so it was trained in one place, but then we wanted to evaluate it on lots of different platforms at lots of different institutions to see if that model could actually control different robots at different places. So for RT1X, which was trained on that subset of the aggregated data set, what we did is we sent checkpoints to the different labs over the internet and had them evaluate those models or those policies at their respective labs. And I should emphasize that there's really no standardization in the control infrastructure, the control stack. This is a single model that was kind of being plugged into robots in different places with different control stacks. The RT2X model is considerably larger than RT1X. So RT1X is like roughly around 30 million parameters, and RT2X is around 65 billion parameters. And so for a variety of reasons, for this model, we didn't send checkpoints over the internet. We actually had an interface that allowed the researchers at institution B, C, and D to send an image and get back an action from that model over the internet. Cool. And then I think that the data set is really exciting because it opens lots of different questions. And we only studied some of the questions in this work. And the reason for that is that a lot of these evaluations take a lot of work, and the total number of evaluations that we ran was around 3,600 across 6 different robots that were represented in the data. Cool. So now let's get to the question of whether or not we can actually have a model that can control different embodiments by training on this data. So we took the RT1X data model that was trained on this data, and we evaluated at those different institutions, like I mentioned. And these are what the results look like. So there's a lot to unpack here. The rainbow curves or the rainbow bars correspond to the performance of that single cross-embodiment model called RT1X. Each of the bars next to that correspond to RT1 trained only on the data from that institution. And then the first bar in each set of three corresponds to the original method that was developed for that particular data set. And so what we see is that first, training on cross-embodiment data actually improves performance over training on in-distribution data. And this suggests that oftentimes when we collect data at our own institutions, probably we aren't collecting as much data as would be useful for these models. And it's not just that RT1 is like overfitting or something to that institution's data. We're also outperforming the method that was developed for that data set, trained on that data set. And on average, the improvement in success rate is around 20%. Cool. So this is, in my mind, a pretty exciting result that we can actually have a model that can run at these different institutions by sending checkpoints over the internet and by having it trained across these different embodiments. Yeah.
What kind of tasks this different labs doing?
Yeah, what kind of tasks are these different labs doing? So it varies pretty significantly. Some of them are pick and place tasks. Some of them are more complex. So this the Rail data set on the Franca was actually a cable routing task that is involves much more precision. So it's a variety of tasks, and it's the tasks that were in those data sets. Cool. And then we wanted to start to look at generalization, and we started. For this, I'll look at the RT2X model, which is co-fine-tuned with internet scale vision language data. And we started by just looking at the evaluations from the RT2 paper. And these are evaluations of pick and place tasks for unseen objects, unseen backgrounds, and unseen environments. And for this, we saw that the RT2X model performs on par with the original RT2 model. This, in some ways, isn't unexpected because RT2 already generalizes fairly well along these axes because it was kind of pre-trained and co-fine-tuned with the web data. I think what's kind of more interesting is we evaluated this RT2X model and RT2 on instructions that weren't in the data set for the Google robot. And so the Google robot was trained on things like pick up an object or move an object near another object, but it never saw instructions like move something to the top right or the bottom right of a counter, or move an object into a pot or near a pot. It didn't see kind of these more fine-grained variation in motion, such as being relative to other objects or with varying prepositions. So that said, these kinds of instructions were seen in data for another robot embodiment, specifically the bridge data set, which has a WidowX robot. And so this experiment is testing whether or not the model can essentially transfer information from a data set on one robot embodiment to the Google robot, which is a different embodiment. And so here's an example video of the RT2X policy. And the instruction here is to move the apple between the can and the orange. There was no data of this robot embodiment for this kind of instruction of moving an object between other objects. And we see that the robot is able to successfully kind of place the apple between the can and the orange. And if we look quantitatively, RT2 naturally really struggles with these kinds of tasks because they're out of distribution compared to the instructions it saw during training. It gets around kind of 25 to 30% success. And in contrast, RT2X is able to do substantially better. It gets around kind of upwards of 70% success, which suggests that it's able to kind of transfer information from one embodiment to this other embodiment by training on the combined data. Yeah.
Say that the RT2X has a compositional reasoning versus RT2.
So when I say that RT2X has compositional reasoning, in some ways this is a form of compositional generalization where you kind of have instructions from one data set and a robot from one data set and it's able to combine that. So in that sense, yes. But there's, this is, I guess, one instance of that, and it doesn't necessarily guarantee that it will generalize in all ways. Yeah.
Is Google data like the only data set within this like big open data set with every annotation?
No, sorry. So all the data sets that RT2X is trained on are language annotated. And so that includes 6 different robots with language annotated demonstrations. Yeah.
Is there any bad data? Would you like, if I have a really bad policy, would you not want my data? Or is the philosophy that you can just take any data as a bad one? And
Yeah.
I feel like if you're learning the policy, you'd be more susceptible to that than if you're learning a dynamics model.
Yeah, so the question was, is there any bad data? So for imitation learning, certainly it's going to rely on having higher quality data. And so far we've only done imitation learning with this data, but I think that'd be really exciting to explore other things like learning dynamics models, like offline reinforcement learning and so forth. The quality of the data is something that kind of like how the data was collected is in the metadata of the aggregated data set. And I think that in the long run, I think that I'd love to see a lot of bad data, a lot of kind of attempts that weren't successful in an aggregated data set like this, because I think that there are a lot of methods that can make use of that. Cool. So the takeaway, at least for me, is I think that large scale data is starting to become a reality for robot motor control. And at the same time, there's also a lot of opportunities for future work. First, the experiments that we did on this data set, there's lots of more experiments and analysis, really interesting experiments and analysis that could be done with this data. I also hope that we're able to continue to expand this data and continue to have the community improve upon this data. And I should mention that I'm really speaking for 170 some different people when I present this work. And I highlighted a couple people that had a particularly active role in the project on the bottom left right here. Cool. Also, if you're interested in joining, you can email this email address. You could also find the email address on the project website. Yeah.
I think you mentioned that the action space is like discretized in this case. How far do you think we are from seeing like generalization across embodiments to like continuous space actions?
Yeah, so the action space is discretized. I think that in principle, you could also do continuous actions. That said, we've also been able to do fairly fine-grained manipulation tasks with discretized actions. And so I don't think that that's necessarily a fundamental limitation. Yeah. Cool. So I talked about training on a broader data set. Now, I think that this is really exciting, but it's also not going to get us there, get us all the way. And one other ingredient I think we need is allowing robots to try to actually generalize to things that they didn't see during training. Now, the idea that I mentioned at the very beginning is whether robots can adapt on the fly with data and experience that they see in the test scenario. And this is also something that, at least to some extent, people do as well. So this is a person opening a door, and if it's a little bit subtle, but if you see when they first put the key in the door, they weren't quite successful, and they didn't quite get it in the right spot, and then they adjust their strategy and adapt to eventually open the door. So humans can do this really, really well, seemingly. And I'm interested in whether we can allow robots to adapt on the fly as well. Now, to do this, in principle, reinforcement learning provides a framework for allowing robots to adapt autonomously from their own experience. But in practice, I don't think it's there in terms of, I don't think it provides everything that we need in order to get this sort of on-the-fly adaptation. So Polkett mentioned back in 2015, we had some work on reinforcement learning that could learn from its own experience and improve and so forth. But I think that we can't yet take these algorithms and just apply them during deployment to have robots adapt on the fly. And there's a number of challenges here. First, these algorithms need feedback, human feedback in the form of some reward function. They also need to autonomously retry the task. And in some tasks, you can kind of hard code that. But in other cases, that means that a human might need to come in and reset for the robot. And also, a lot of the reinforcement learning algorithms learn from scratch. And for adapting on the fly, we want it to start from what it already knows and be able to leverage that when adapting on the fly. So you might ask, well, some of these challenges seem like maybe existing RL algorithms can still handle this sort of reset-free, autonomous adaptation scenario. But if you take even a really simple RL environment, this fish environment from DM control, if you give it resets every 1,000 steps, it works okay. But if you reduce the number of resets that it's given, it really starts to struggle to actually learn a performant policy. And so I think that the existing algorithms that we have aren't kind of well suited for handling these other scenarios that we might care about in robotics. So I think we need some alternative paradigms for allowing robots to adapt autonomously from their own experience. One paradigm that we've looked at is reset-free reinforcement learning, where instead of having a human come and reset, the robot actually practices both learning the task and learning to undo the task so that it can keep on practicing without a human intervening. And then a third paradigm that we've looked at is that I'll talk more about today is what we're calling single life reinforcement learning, where the robot has some previous experience and maybe it can already do the task to some degree. But then if it encounters an out of distribution or a new scenario, we want it to be able to still figure out how to solve the task in that new scenario. And so what we're imagining is something where you have some previous experience, then the robot's in a new scenario, and it needs to figure out on the fly how to do that task in a single episode or in a single life. That's what we call it, single life. And so specifically, what we're considering is we have data in some train environment or multiple train environments, and the agent has one life to autonomously complete the task in a novel out of distribution scenario. Cool. As one example, you could imagine a really simple simulated environment. We'll get back to real robots in a minute, where its training experience is just on a single plane. And then maybe in its test environment, there's an obstacle, and it needs to figure out how to get over that obstacle. Now, you might ask, well, maybe we can just run reinforcement learning at test time in order to have the robot learn this new scenario. And if you do this, if you train the robot in the kind of the training environment without any obstacles, and then you put it in this new environment and fine tune online as it's collecting new experience, what will happen is it will end up in a state like this, and it'll keep on trying to get towards the goal and move forward. But the algorithm will eventually get stuck, and the robot won't be able to figure out how to kind of get back up and eventually handle this new scenario. And so existing reinforcement learning algorithms don't allow us to have robots actually adapt on the fly during deployment to new scenarios. Now, I think that this is a really interesting problem setting, and I don't think that we've solved it, but I think we've been able to make a little bit of progress towards solving it. And one idea that we had towards this is to actually have robots not just adapt in the low-level action or parameter space, but also to adapt in a higher level space of behaviors. And in particular, if the robot has some pre-trained behaviors, like it knows how to walk, it knows how to slide, it knows how to crouch, we want the robot to be able to both adapt its parameters at test time, but also adapt in the space of these behaviors to figure out how to handle a novel scenario at test time. And so our problem setting is we have some pre-trained behaviors, and then during a single episode at test time, we want the robot to be able to handle typical conditions, but also to be able to handle slippery conditions, a damaged leg, maybe a damaged leg and some sort of payload on the robot, and so forth, including conditions that it never saw during training. Cool, so that's the problem setting. Now, we need, kind of for this problem setting, we need to be able to figure out which behaviors are relevant at each given point in time, and then also be able to fine tune those behaviors. With fine tuning, we can use we can use reinforcement learning algorithms to fine tune the parameters, but we need to figure out which behaviors are relevant. And one really simple idea is we could use the value functions of each of our prior behaviors to select which behavior is relevant. And naturally, the value function for a given behavior, if it thinks it can succeed in that scenario, the value function should be fairly high. And so if we have, for example, walking and limping, the value function, we can just look at the value function for the V that's higher for our given state and choose that behavior, and then also fine tune that behavior. So this is one approach that we can use without actually making any alterations to the training process. But one additional thing that we can do is we can also encourage these value functions to be able to identify the states that it was kind of trained on. So we're going to add an additional loss that encourages it to the magnitude of the value functions to actually be able to identify whether a state is from the walking skill or whether a state is most relevant to limping. And this ends up being actually really simple. So you have your standard Bellman objective for training the value functions, but then you're additionally going to have a standard cross entropy loss, like a classification loss, that trains the base on top of those value functions, that trains it to be able to classify for each of the data sets for each skill, which skill did that state come from. And so this will essentially train each of the behavior's value functions to be able to identify states that are familiar for that skill, and thus be able to actually select which of the skills are going to be relevant for this new scenario at test time. And then once we have these value functions for each of our skills, then at test time, at each time step, we'll get a state. We'll then sample a skill from the classification distribution to pick which skill to use. And then we'll additionally fine-tune that particular skill that we chose at test time on the fly as well. So at every time step, we pick a skill, we execute an action, update that with a fine-tuning objective, and then move on to the next step where we potentially pick an entirely different behavior. So with this approach, we're able to actually adapt at each time step both the behaviors as well as the parameters of those behaviors to handle kind of both higher level shifts and lower level shifts that we might encounter at test time. Yeah.
Are you assuming that in your distribution of things that you can encounter in the wild, that you have a skill that addresses that observation?
Yeah, so are we assuming that we have a skill that addresses one of the test time scenarios? Yes and no. So we're assuming that we have some skills that are fairly diverse as pre-trained behaviors, but they may not address exactly that behavior. And so there's a couple of things where this can be useful. First, you might encounter a test time scenario where one skill won't cut it, but the combination of a couple of skills, applying them in sequence, might help you get out of that scenario. And then second, we're additionally fine-tuning each of those behaviors. And so in our experiments, we're actually going to be testing on scenarios that are out of distribution, and that fine-tuning is very helpful as well.
Yeah, I was just curious if you wouldn't want to maybe ensemble over possible skills in order to get that heterogeneity in your action space, rather than trying to select a discrete skill at one point and then another one at another time. I think there's some efficiency gains.
Yeah, definitely. I think it'd be interesting to try to ensemble in some way. Maybe you could even ensemble relative to the predicted probabilities in the probability distribution. We haven't tried that, but I think it'd be pretty cool to try. Awesome. And so compared to some prior approaches, there's actually a lot of prior work that tries to adapt to new scenarios. Some of it would try to have a high-level controller that picks which behaviors to do, like in hierarchical RL. In this case, we actually don't need to train a separate high-level controller, and so it's a lot simpler from that standpoint. In contrast to meta-RL approaches that will try to kind of explicitly optimize for adaptability of different policies, this approach is much more agnostic to how the policies and value functions are trained, which makes it a little bit easier to train those policies and value functions for the prior behaviors. And then overall, it's a fairly simple mechanism for adapting within a single episode to a variety of scenarios. Cool. So how does this compare to prior methods? In simulation, we started with evaluating the number of steps to succeed. This was on a simulated Go1 robot, so a quadruped with varying joint stiffness and varying ground friction. And the skills that the pre-trained skills that it has corresponds to kind of having different joints that are frozen during training. But then at test time, a new joint is frozen. And then for friction, the skills were trained with varying amounts of friction for individual legs. And at test time, we see a lower friction than anything that was seen during training, as well as different combinations of legs with that lower friction. We compare to a state-of-the-art fine-tuning method, a state-of-the-art kind of meta-RL style method, as well as using a high-level classifier to predict the skills. And first, looking at these prior methods, we see that in some scenarios, for stiffness, it works best to adapt in the space of behaviors using the high-level classifier. And we see that on the right, for friction, it's actually best to use the RMA approach, which would adapt more at a low level. And so we actually see that in different scenarios, it's beneficial to adapt in different ways. And then for Rome, which is shown in yellow, we actually see that by adapting both in this higher level space and this lower level space, we're able to get around 2x faster adaptation. It's able to kind of get to the goal 2x faster compared to approaches that try to adapt just in one space versus the other. Yeah.
Are your variance bars in the last plot only like about different trajectories starting from scratch and doing wrong for one objective or multiple objectives?
So the different bars are over actually different different test time scenarios. So we run multiple single life episodes at test time for one test scenario, but also over actually multiple different test scenarios that are held out from training.
High variance like amongst scenarios or amongst?
Do we see more variance among scenarios or within a scenario? So I think that there is definitely some high variance even within a scenario, because in some cases the robot will just get stuck and just like not take a really long time to complete the episode. And so there's a lot of variability there. Cool. And then can this method work on a real robot? So we took a real Go1 robot that we got fairly recently. We pre-trained behaviors with walking with different legs frozen. So there's 5 different pre-trained behaviors, one that walks normally, one that was trained to walk with the back left leg frozen, one that was trained to walk with the back right leg frozen, and so forth. And then we looked at 3 different test scenarios that were pretty different from anything that it saw during training. So during training, it was just walking on kind of a flat surface as normal. And the first scenario that we looked at was to put roller skates on the front 2 feet of the quadruped. We had to buy kids roller skates because the robot's legs are a little bit small. And if you just evaluate the walking controller, it basically falls over immediately. It isn't able to handle this out of distribution scenario. The high level classifier is able to do a little bit better, but it decides that it's really not up for the task pretty quickly. And then this is with the approach that I mentioned, where we're adapting at both a high level and a low level, and we see that even though the scenario is really out of distribution compared to what it was trained on, it's able to adapt on the fly within this single episode. Cool. We also looked at some other scenarios. So we looked at carrying heavy luggage. So in this case, heavy luggage is tied to the back left leg of the robot. And again, the robot is able to, even though it didn't see any luggage during training, it's able to lug this heavy luggage. It corresponds to around 13 pounds. And in this case, we started with the heavy luggage, and then we removed the backpack, which is actually quite heavy. And you see that the robot is able to handle that dynamic load and also actually speed up a little bit with the new scenario and adapt once we then put on another heavy backpack. Yeah.
I'm not sure if you mentioned this, but where did you get the pre-trained skills from?
Yeah, so for these skills, we actually pre-trained them with an efficient reinforcement learning method in the real world. We were also looking at using pre-trained behaviors in simulation, but this actually ended up working the fastest for us.
Like how many skills were there?
Oh, 5 skills. Walking and then walking with different legs, with the joints of different legs frozen. Cool. And so, yeah, this was an approach of not just training on a large data set, but actually trying to see if robots can generalize beyond the scenarios that they were trained on. And by adapting both at higher levels and lower levels, we're able to allow these robots to handle out of distribution scenarios. Yeah.
So in the RTX world, you've got one massive transformer that's being conditioned, and this time you've more explicitly factored into the skills. Is there a reason that you prefer one or the other?
Yeah. So it's a good question. I guess we could have had like a single language condition policy in this latter case. We only had 5 different skills that's all we ended up needing in order to get good performance for these scenarios. I think that in the long run, I would love to have more than just 5 prior behaviors, and we're actually talking about some future projects where we where we would have a much wider set of skills. And in that case, I think that just training a single model that's conditioned on the task or conditioned on a language description or something might be a little bit easier than training them separately. But yeah. Cool. And then in the last like 5-10 minutes, I want to get back to dexterity. So I talked a lot about generalization, and the kind of dexterity of the skills in the first work, especially where it was fairly low, mostly like pick and place style tasks. And I think it's also important to not just have robots do pick and place tasks and actually try to do more challenging tasks. And I'd love to do this in a way that in the long run would actually be able to get both complex skills and skills that generalize well. And in order to do this, I think we need to have fairly scalable data collection approaches, because to get the kind of generalization we need, we be helpful to have a broad data set, a large data set. And so to be able to scale data collection, I think it'd be really helpful to have a low cost setup with teleoperation that is very easy for people to use, that doesn't take a lot of time to collect a demonstration of a single task. And ideally a setup that's capable of doing complex tasks in the first place. And so this is where this hardware setup comes in. So Tony here is kind of, you can see him teleoperating the robot to do lots of different tasks. This is a setup that we call Aloha, for a low-cost hardware for these kinds of tasks. And in some ways, the video, I think, kind of shows the breadth of skills that this hardware is capable of doing. And one thing that I think is exciting is that the total cost of this entire platform is around $20,000, which is less than the cost of a single Franca, for example, at least in the US. And also the robots here are off the shelf, and all the white parts are open source, the kind of additional components on top of it. And it's also just a lot of fun to play with. Now, when we first started this project, I actually didn't think that these arms, I wasn't very that impressed with these arms. I didn't actually think they were that capable. And also the manufacturers of the arms also didn't think that they were this capable. So they were pretty surprised that the robots were able to do this. So this is the hardware setup. The way that the teleoperation works is really simple. We record the joint angles on the robot, like the leader robot that the human is holding, and then we tell the follower robots to go to those joint angles. It kind of bypasses any sort of inverse kinematics, which is helpful because these arms don't have any redundancy. Yeah, and you can write this in 3 lines of Python code. Really simple. We command joint angles. We kind of record and do this mapping at 50 hertz. Of course, there's a lower level controller that operates faster than that. And then we are recording RGB images from 4 different cameras, from a camera facing backwards, a top-down camera, and 2 wrist cameras. Now, one thing I'd love to highlight here is that there's a lot of complex tasks that this hardware is capable of doing, and we're actually not using any force feedback or any tactile feedback. And to some roboticists, and to myself as well, I think that this has been actually somewhat surprising. And we actually tried to push this even further and see what tasks we think would really require force feedback and tactile feedback, and see if the robot can do it. And so here I'm teleoperating the robot to peel the shell of a hard-boiled egg. And with some patience, you can actually do this fully from end to end on the robot. And by that I mean from the hard-boiled egg to a fully peeled egg. Certainly tactile feedback I think would allow you to do this faster, but it suggests that it is possible to do this. And you could also do something like taking a contact lens out of a container. Cool. Now, there's a question of now we can kind of collect data for these fairly complex tasks with objects that are difficult to simulate. Now, can we actually train a policy to do these tasks? And we're going to be training a neural network policy that maps from images to the target joint angles. And with this setup, we actually have a couple challenges that come up. We're doing this at 50 hertz, which is a lot higher frequency than all the other robots. And so compounding errors is kind of a known issue with imitation learning, and it is exacerbated with this higher control frequency. And second, human demonstrations perform tasks in different ways, and this means that the data distribution is a little bit multimodal. As a result of these, we actually tried taking multiple prior methods, and we actually tried pretty hard to get them to work on this setup. And we found that these prior methods, even with careful tuning, all got 0% success on the real robot tasks. And so to do better, we tried to actually alter the imitation learning approach. And the number one kind of key thing that we did that really made this work was to chunk the actions. So instead of having the policy predict one action at a time, it predicts a chunk of, say, around 60 actions or 100 actions. And it predicts that chunk and then executes those actions open loop. And then after it executes those actions open loop, it gets the new image and then predicts the next chunk of actions. This kind of visually looks like this. And we found that essentially by making it a little bit more open loop, the policy works substantially better with this kind of chunking than without. And you can combine this kind of chunking with not just with our architecture, but with other architectures as well. Now, to not make it entirely open loop and to make the behavior a little bit smoother, we actually, on top of predicting these chunks of actions, when we execute an action, we actually will average or ensemble the predictions for a current time step, and then execute that average, that weighted average of actions. And we found that this led to smoother behavior and nicer behavior. We also use a transformer-based policy architecture. In some ways, it's not all that different from the RT1 architecture, but this action chunking is a really key component. The actions in this case are going to correspond to absolute joint angle positions, and we're going to use a variational autoencoder to model the multimodality. Cool. And so on the real robot, we collected 50 demonstrations for a number of different tasks, trained the policy on that single task on those 50 demos. And in the demonstrations and at test time, we randomized the object location along the white line. So these are fairly narrow skills. And hopefully, as we scale up data, we can actually start to generalize much further. And so we see the robot can do fairly delicate tasks like taking this lid off of the cup. The success rate of this policy is around 84%. We also did this task of slotting a battery into a remote control. And for this task, there's a spring in the battery. So you have to kind of slot it in and then actually, first put it down and then actually slot it in fairly delicately against that spring in order to successfully insert it. This policy has a success rate of 96%. This task is one of my favorites because I think it would be very hard to simulate the objects in this task. So the robot needs to tear off a piece of tape and put it onto a box. Getting the tape teared in the right position is actually fairly precise because if you put it not on the metal part, then it won't actually tear successfully. The handover actually also is fairly challenging for the imitation learning method because people will demonstrate the handover in different places. And then lastly, there's also a shoe task where we put a shoe on a fake foot. And here, this was one of the longer tasks. It needs to, of course, position the shoe, but also put the Velcro flap onto the top part of the shoe. I'm a little bit low on time, so I think I'll skip the rest of the video. Now, I also wanted to briefly, I don't have time to get into the details of this method, but in follow-up work, we kind of combined this sort of action chunking method with an approach for extracting waypoints, especially with a focus on longer horizon tasks. So this was one task we looked at, but we also looked at making coffee with a K-cup machine. Probably not very good coffee, but coffee nonetheless. And for this longer horizon task, we're also able to do tasks like this, although waypoint extraction here is really helpful for doing this longer horizon task. Cool. And then lastly, here's one quantitative evaluation looking at the importance of action chunking. And we see that when you are fully closed loop with a chunk size of 1, the performance is really, really low. And then it is a lot higher once you increase the chunk size. Okay, so the takeaways of this last part is we can learn narrow skills from around 50 demonstrations. Low-cost hardware is actually surprisingly capable, and force sensing doesn't seem perhaps as critical for these tasks as we might thought. And then imitation learning, we found that action chunking is really helpful for these fine-grained, high-frequency control problems. There's also a lot of limitations with this. For this platform, some tasks might require more than 2 fingers, might require force, or some tasks require fingernails. And the reactiveness to stochastic events or really greater variation requires more data than the 50 demos that we were giving it. So yeah, overall, I talked about broader data sets, generalizing beyond the training distribution, and also dexterity. I think that in the long run, I'd be really excited to see some of this dexterity actually plug into our data sets and try to actually get dexterous and general policies at the same time. And hopefully some of the folks also working on really long horizon planning can actually then use these motor skills to actually have robots be useful in the real world. I like to highlight a lot of the students in my lab. I also highlighted previously a lot of the students working on the cross-embodiment effort. And yeah, happy to take a couple questions. Thanks, everyone. Yeah.
So what do you think the role of simulated data?
Yeah, so what's the role of diverse simulated data in cross-embodiment?
Yeah, the past grade still data question.
Yeah, so we can get a lot of data from simulation. I'm not sure if we can get a lot of diverse data or a lot of the right data that we need. But I do think that simulated data, it makes a lot of sense to add simulated data or add diverse simulators to this. I've been kind of mostly dedicating my efforts to using real data because I think that in terms of machine learning, a lot of the advances that we've seen have been using real data. And there's also lots of scenarios where it's very challenging to simulate, like tearing off a piece of tape or skewering a grape with a fork or something like that. But I think that I hope that more people in the community will also investigate simulated data. Yeah.
So the OpenX data set is covering like around 300 scenes, right?
Yeah.
I'm wondering, like, if you actually want the robot to learn from your data set and generalize to unseen violence or object, like how many such scenes would you expect the data set?
Yeah. So the question was, how many scenes do we need to generalize? I don't know. I think that it'd be worthwhile to try to do some analysis, like looking at trends as you scale up, like numbers of scenes, number of data points, and so forth. The first effort that I mentioned, the data collection effort, there we actually already have. Well, it's hard to count scenes, but we already estimate having around 600 scenes, and that actually is so far a much smaller data set so far. And so I think it might be more than 300, and I hope that that data will continue to grow, and also that we can have a targeted effort of having a lot of variation. But yeah, estimating the quantity and diversity of data is hard. Yeah.
So I'm interested in that online adaptation part, right? So if you look at the person with the key, which is a really great example. Right, on the one hand, they're clearly adapting. On the other hand, they have done this adaptation before, probably, right? So what's interesting is the degree to which you can keep that alive, right? Like, so you say, oh, I have this problem putting keys in locks. And yay, I got the key in the lock this time, but then I wanted to be better at putting the key in the lock next time. So the question is, how do you think about like a basis set of behaviors or something that you could keep around so that every single task is not a new thing, even if it's an adaptation of something.
Yeah, so I think that like ideally we'd have lifelong learning systems that can figure out when to add new behaviors and when those new behaviors will be kind of orthogonal to what they have so far. I don't know if I have a solution for that exactly. Like thinking about behaviors and so forth. Like we've done a little bit of work on like lifelong learning and adding new skills and so forth. But a lot of what we've done so far is somewhat manual and has a human involved. Like you just have a new thing that a human says, like, I want you to do this, and then you kind of naturally add a skill for that. I don't know if we need it necessarily for the robot to figure out whether or not it should add a new thing or not. It's possible that supervision can be helpful for that. But certainly I think that it makes, like, I would love to have kind of a diverse basis of behaviors like you described.
So model, how was the training data nature? Was data model?
The robot data?
Yeah, like determining the nature, like say nature ratio or base of the data from.
Yeah.
Because I wonder if that's always a problem for say other.
Yeah, so for RT2X, there actually wasn't any iteration on that. Actually, there was no iteration. There was just one RT2X model that was trained. And so it's likely that the particular mixture that was chosen is not the best mixture because there was no iteration on it. It was somewhat, I guess it was like human guided, of like you want it like but so there's human guided intuition, but there was no iteration on it, and there's probably room for improvement. There is some work by some folks at Stanford that tries to actually optimize for the mixture. I think it's called Doremi. Yeah, exactly. Yeah.
How much do you think the insights you're taking from this like one line perspective should be transferred to general how we measure performance in machine learning systems? That's to say that we should consider that we can always provide some kind of one iteration update and instead of fixed accuracy numbers.
Yeah, I think that a lot of machine learning systems are deployed as static systems, and we've also been thinking a little bit about about some of these ideas in like more standard supervised learning scenarios as well, where you can adapt. In some ways, adaptation is actually more natural for robots than for machine learning systems, but I do think that these more sorts of dynamic things make a lot of sense. I don't think there's any consensus on the way to do that. Fine tuning is one very popular way, obviously, of kind of adapting a little bit. But I think that, I think that we should always be rethinking the way we evaluate things. And in some ways, I actually don't like that machine learning is so benchmark driven, because I think it makes people conform to a particular style. And I think that we should actually innovate more on how these systems are evaluated, because this kind of adaptation may actually lead to a lot better performance, possibly. Okay, maybe we should end there.
Let's hand the speaker now. Thanks, Sophie. Sorry,
And the questions were good, so it seems like people were paying attention.
They were engaged.
I was a little bit worried about how long I'd made the talk, but
yeah, I can never predict how long my talk is going to be. I'm so bad at that.
yeah.
So we plan to make the GPT for robotics,
Maybe.
scale up data. Cool. So I'll let you talk to people, and then Marcel will take you for lunch with students.
Okay, and then we'll chat later today.
Yeah, we'll chat.
Awesome. Okay.
See you.
Thank you.
Yeah.
So that's for part two. I have a very minor question. So for the part two, we talk about how the basic skills.
Yeah.
But like given a task, how do you choose the basic skills?